Hello everyone, today I'm introducing the order. So the order is another important concept in congruences. Let's first look at the definitions. The definition of order is that if A and n bigger than 1 are relatively prime integers, then we have infinite number of k such that a to the k is congruent to 1 mod n. We define d equals to the order of a modulo n such that a to the d is congruent to 1 mod n, and d is the smallest value of k. So the order of a modulo n, which is d, has many important properties, and let's look at these propositions. So here are the propositions of order. First, let m be a positive integer, then a to the m is congruent to 1 mod n if and only if the order of a modulo n divides m. The next one is since a to the phi n is congruent to 1 mod n. This is what we learned in Euler's theorem. We have the order of a modulo n divides phi n. Next, let d be the order of a modulo n, then order of a to the k's power modulo n times the GCD of d and k equals to order of a modulo n. The last one, let d be the order of a modulo n and c be the order of b modulo n, then order of ab modulo n equals to cd. This need to be the case that the GCD of c and d equals to 1. So here are the 4 propositions of order. Now let's see some questions. So the first question is to determine the order of a modulo n if a equals to 2 and n equals to 3, 5, 7, and 15. So first, we know that the phi of a prime number, which is 3, equals to p minus 1, which is 2. So we learn from the prepositions that the order of a modulo n divides phi of n. So this means that the order of 2 modulo 3 divides 2, and 2 is a prime number which equals to 1 times 2, so we only need to check 1 and 2 at this case. So 2 to the 1 does not congruent to 1 mod 3. This is not correct. And 2 to the 2, this is congruent to 1 mod 3. So the order of 2 modulo 3 equals to 2. Next, we know that phi of 5 equals to 5 minus 1 equals to 4. Then the order of 2 modulo 5 divides 4. So we only need to check 2. 2 to the 2 is not congruent to 1 mod 5. Thus, in this case, the order of 2 modulo 5 is 4. This is true because of the Fermat's-Liouville theorem, which because 2 and 5 are relatively prime, thus 2 to the 5 minus 1 is congruent to 1 mod 5. Now let's look at 7. you know that phi of 7 equals to 6, and you only need to check 2 and 3 because 6 equals to 2 times 3. So 2 to the 2 is not congruent to 1 mod 7, and 2 to the 3, this is congruent to 1 mod 7. So we have order of 2 modulo 7 equals to 3. Last but not least, we have the phi of 15. This equals to 15 equals to 3 times 5. Thus, the phi of 15 equals to 15 times 1 minus 1 over 3 times 1 minus 1 over 5, which equals to 8. Now, for 8, we have 8 equals to 2 times 4 and nothing else. So we check 2 first. 2 squared does not congruent to 1 mod 8 mod 15. And 2 to the 4th, this is congruent to 1 mod 15. Thus, the order of 2 modulo 15 is 4. So we are finding the least number of k on the exponent that 2 to the k is congruent to 1 mod n. So we only look at the divisor of that number, the phi of that number. In this case, the phi of 15 is 8, so the only divisor for 8 is 2 and 4. So we check 2 and we check 4. If those does not happen, then we can conclude that it is 8. Yeah, let's look at the next question. Next, determine the order of a modulo n if a equals to 5 and n equals to 7 and 29. So first, if n equals to 7, we have phi of 7 equals to 6, and we need to check 2 and 3. Obviously, 5 to the 2 is not congruent to 1 mod 7, and 5 to the 3 is not congruent to 1 mod 7. So after we check 2 and 3, we can conclude that the order of 5 modulo 7 is 6. Now let's look at 29. The phi of 29 equals to 28, and 28 has divisor of 2, 4, 7, 14. And so first, 5 to the 5 squared is not congruent to 1 mod 29. It is congruent to negative 4 mod 29. Thus, if I square on both sides, we have 5 to the 4th. This is not congruent to 29 as well. Now let's check 7. So we times 5 squared on both sides. So 5 squared times 5 to the 4th equals to 16 times negative 4, which is negative 64, and we times 5 on both sides. We have negative 320, and 320 and 29 does not divide 320, so we eliminate 2, 4, and 7. Now let's look at 5 to the 14th. 5 to the 14th equals to 5 squared to the 7th, which equals to negative 4, which is congruent to negative 4 to the 7th. And negative 4 to the 7th, this equals to negative 4 to the 3rd times negative 4 to the 3rd times negative 4. And we can eliminate these two negative, and 4/3 is 64, and 64 is congruent to 6 mod 29. Thus, this is congruent to this number. is congruent to 6 times 6 times -4, and this equals to 36 times -4, which is -144. 29 does not divide 144, so we eliminate 14 as well. So it follows that the order of phi modulo 29 is 28. The next question, let a bigger than 1 and n be positive integers. Show that n divides the phi of a to the n minus 1. So first, if we have a to the d, if we want to find the order of a modulo a to the n minus 1, we have a to the d is congruent to 1 mod a to the n minus 1. Thus, it follows that d equals to n. Why is that? Because if d equals to n, then this becomes a to the n minus 1, and a to the n minus 1 is obviously the smallest that can divide a to the n minus 1. So we have n equals to d, and d is the order of a modulo a to the n minus 1. And we learn from the properties that order of a modulo n divides phi of n. So phi of a to the n minus 1 is divisible by n, which n equals to d equals to a order of a modulo a to the n minus 1. So the order of a modulo a to the n minus 1 divides phi a to the n minus 1. That's the same as the properties. Let's look at the last question. Determine all positive integers n such that n divides 2 to the n minus 1. So for positive integers, let's first try n equals to 1. This is obviously true because 1 divides 2 to the 1 minus 1. However, for n equals to 2, we have 2 squared minus 1. This is an odd number, so 2 must not divide this number. Therefore, we find out that n must be odd. Now let's try to use the order to find this question. See if any n bigger than 1 and is an odd number that meet these requirements. So first, we have 2 to the n is congruent to 1 mod n. Let's first let p be the smallest prime divisor of n. Thus, it follows that 2 to the n is congruent to 1 mod p. Then the order exists, that order of 2 modulo p less than this equals to d. So let's find the properties of d in these questions. First, d divides n. Why is that? Because of the definition. So d divides n, this means that p is less than or equal to d, because p is the smallest prime divisor of n. Next, d divides p minus 1, because p is a prime number. Therefore, we have the Fermat's-Little theorem that 2 to the p minus 1 is congruent to 1 mod p. Thus, d is less than or equal to p minus 1. Next, we have GCD of n and p minus 1 equals to 1. Because p is the smallest divisor of n, so p minus 1 must not divide n, so they are relatively prime. Therefore, we have this conclusion. And p is less than or equal to d, where d is less than or equal to p minus 1. So there's a contradiction, so there is not such n exist. Thus, this question, only number 1 can meet these requirements. So the answer is n equals to 1. So if you have any questions, please contact my email, and see you next time.